Hello everyone. So today let's work on a crank slider inversion program, and you might have already seen these in one of those additional lectures. And in this video I'm going to show you something different. So instead of creating this T-shaped output link in Simscape, what I'm going to do is trying to create such a model in SolidWorks and import it into Simscape. So first of all, let's create an empty Simscape model. You can type in smnew in the command window, and you're going to see something like this. And I've already worked a little bit on this model, so we can move forward in a higher speed. So first of all, you go to the workspace, the model workspace, and you define all the parameters. So these parameters you can find in the PDF file, and the length of the ground bar, length of the input bar is L2, length of the coupler, and then geometry of the output link is given. So we assume all these linkages, they are made of steel, so the density is 8,000 kilogram per cubic meter, and the rotation input is theta2, and it's a constant speed rotation, and then the speed is 0.4 pi radian per second. Okay, so once you have all of these ready, so what we need to do is create all these links in Simscape. So you already learned how to do these in previous videos, and I'm just gonna show you how everything is set up. So because all the links we're having is they're rectangular bars, so we select the shape as brick, and then the dimension is length L2, width, depth, and the cross section is defined by width and depth, and then it's 0.1 by 0.1. And in the inertial tab, we need to change the density. By default, the density is 1000, and let's change it to rho, which is 8,000 as we defined. And there's one thing special I need to emphasize, which is the derived value. If you click this plus, and then you can see there is an option you can click update, and there are separate options. So first of all, the mass, showing the total mass of this link in kilogram. The center of mass means where the center of gravity is. So in this case, it's all 0. That means the center of mass is at the origin. You can find the origin by clicking this coordinate bar. And the moment of inertia. So you have 3 different values. So the first one is IXX, IYY, and the last one is IZZ. So that means what is the mass moment of inertia around X, Y, and Z axis. So usually I would recommend you to change the color of each link. So for input bar, I will use blue. So in such a way, it's more convenient to do your code debugging. So once you have all of this done, so we first create the link number 2, and then we use the same method to create link number 3, which is this coupler. Okay, and once we have all of these solids working, then we can create this T-shaped output link. So I already give you the SolidWorks model I created. The name is output link crank slider inversion 3D object, and you can create your own SolidWorks model by yourself. So the way we import SolidWorks to Simscape is using 2 file formats. So you can either use STL or use step. So I provide both files in the file folder, and in this case I'm going to use the step one. So what you do is go to your shape, find from file, and then you need to change the file type, and in this case we're going to use step. And then the last option is where to find that step file. So if you click here, and then you find this model with appendix of .step, and then click open. And then once you overdone these, you click update, and then you're gonna see the 3D geometry on your right hand side. So after that, what you need to do is you need to change the density, and also I would suggest you to change the color. Okay, so up to this point, we create all the links that are needed for this simulation. So after create all our solids, so what we next need to do next is to connect these geometries following these schematics. So first of all, let's considering this O2 joint. So as I mentioned before, any joints in Simscape connects two coordinate system. So in this case, your O2 connects the ground coordinate and the coordinate of your O2 link. So that's why, first of all, let's create a revolute joint. And for the convenience of future debugging, I would suggest you to name all your joints properly. And the left-hand side of your joint is connected to the ground. So base to the ground. But where to connect the other side of the joint? Because as we mentioned before, when you create a solid link number 2, the center of these, so you can double click it and check the coordinates of this link number 2. So the default coordinate is actually at the origin, which is the center of the link. However, if you look at this PDF file, we want to connect our O2 joint to the left-hand side of the link number 2, which is the location in here. So if we directly connect your follower output to link number 2, that means your joint is actually connected to the center of the link instead of the edge of the link. So how can we make the proper connection? So the method is using the so-called rigid transform, something like this. And in previous videos, I directly show you how much we should shift and along which axis we should shift. But for a complex system like this, how can we tell what kind of rigid transform we should input? So the way I would suggest you to do is, you don't care about the rigid transform first. You initially directly connect this output to whatever you want to connect and give it a shot. Okay, so after you're doing that, you're going to see something in your Mechanics Explorer window. And then, as I mentioned before, the joints connects to coordinate system. In this case, it connects the follower of the O2 joint. You can find it in here, the follower of the O2 joint and the coordinate system of link number 2, which is here. You can see that they're overlapping, but what we need to do is we actually want to connect to the left-hand side. That means we have to shift everything. We have to shift this blue bar along X direction by half of the length. So that's why your rigid transform should be along standard X, going to X axis, and then the offset is half of the length. Then you can directly drag these transform on top of this line, and then everything is automatically connected. And then in this case, if you click run again, you can see that how this rigid transform moves your blue link from the original position to this new location. So we just connect the first joint. So how about the second joint, joint A? So it's the same thing. We first create a revolute joint and then name it as joint A. And then let's look at how this joint A is connected. So first of all, on the left-hand side, your joint A is connected to your input link number 2. And then on the other side, your joint A is connected to this L3. So we know that we need some rigid transform, but we don't know exactly how to transform it. So no worries. So we first connect everything and then click run to see how things are connected in this way, and then we can make changes. So what we do is we go to, after click run, we go to the model. We actually go to the solid mechanics explorer, and then you can see everything is oriented in a very weird way. So first of all, let's try to do some rigid transform between link 2 and revolute joint A. So as I mentioned before, so we actually need to look at 2 coordinate systems. So the first coordinate system is the link number 2 system, which is here. And if you look at here, that's actually in the center of the blue bar. And that's connected to the base of your joint A. So we find the base of your joint A. And as we mentioned before, we need to move these coordinates to the edge of the link. That means we need to shift everything along the X direction by half of the length of the blue bar. So that means we need another rigid transform. So that is along the X direction, and the offset is half of L2. So that connects your R2 coordinate to the joint A coordinate. So you just drag and put it on top of that line. And then in this case, you can click run again. So you see that right now, your coordinates, your base is on the edge of the blue link now. So the next thing we need to connect is we need to connect the follower to the edge of the link number 3. So we need to find the coordinate system for link 3. And then we need to find the coordinate system for your base. So in this case, there is a your link number 3 coordinate, link number 4 coordinate, they're overlapping, but we know that we want to connect your follower output here, this coordinate, to this edge. So that means what we need to do is we need to move this green bar to the right-hand side by half of the length of L3. And because your right-hand side is the X positive direction, that means your rigid transform should be along the X positive direction. You find your standard axis, find the X positive direction, and then shift it by half of the length. Click OK. And then you can put it on top of the line. So the thing is, when you're doing coordinate transformation, so you have to pay attention to the B and F of the rigid transform. So when you connect to B and F in this way, that means you always want to move the target that is connected to your follower by the amount of transform you defined. For example, in this case, your base is connected to joint A. Your follower is connected to link 3, which is the green bar. So that means we need to move your green bar, which is connected to your follower, and such that your green bar is in the right position. So in this case, the right position for your green bar is the edge of the link. So we need to move the green bar such that the edge of the link overlaps with your follower. And that's why we need to move everything along the x positive direction by half of the length. Okay, so we can click run, and you see everything is connected correctly. So the next joint is the slider or prismatic joint. It's very complicated, so we're gonna do it in the end. So then we just create your O4 joint. It's another revolute joint. Okay, and then we name it as joint O4. We know that your O4 is connected to the ground, but not the same ground, because we have to consider the length of the ground. So that means in order to connect the O4 to the ground, we have to first shift the ground by L1. So the shift is along the x direction. So we can easily define a rigid transform. And then we name it as ground. And in the translation, you select standard axis, x-axis, and then the offset is the length of your input link. So your base connects to the O2 ground, and then the follower connects to your O4. So right now we have the joint O4. We need to connect our O4 to these output link. So first of all, we need to double click and check the output link, and we find where the coordinate of the output link is. So in this case, because when I create this T-shaped link, I automatically choose the edge as the origin. So that means we don't have to do any translation, coordinate transformation. But the other thing we need to pay attention is, if you double click your revolute joint, you can see that by default, this joint is rotating around z-axis. That's Z revolute joint. So that's okay for the ground side, but then if you look at your link number 4, we actually want this link to rotate around the green axis, which in this case is our y-axis. So how can we change the axis of rotation? So what we need to do is we need another rigid transform, because we want to change the coordinate. So that's a kind of a special rotation transformation. So we go to the rotation, choose the method align axis. So the best way to do it is we just switch the y and z coordinate, right? So your z becomes x, your z becomes y, and y becomes z. And in such a way, if you connect in here, that means after this transformation, your rotation is no longer around z, because your rotation is around y, because your y becomes z and z becomes y. And then you can directly connect your follower to the solid. And let's see what's happening. And you can click C. It's not that easy to tell, but these coordinate is correctly connected. So the last step, we need to connect this prismatic joint. Because it's sliding, what we need is a prismatic joint. And let's name it as sliding. And then if you double click that sliding joint or prismatic joint, you can see that by default the sliding is always along z direction. So let's check if that's the case for this coupler and the output link. So we double click the output link. We note that the blue line indicates the z direction. And if you check the sliding, the slot on this block, So that Z direction is actually the sliding motion we want. So that's why between link number 4 and the sliding joint, we don't need any rotation, but we need to shift these coordinates along X direction such that your coordinate is at the center of the slot. So that means we only need a linear rigid transform, which is along X direction. Then the offset is L4. So depending on how you create your SolidWorks model, you might need to use a different value. But in this case, in my model, I just need to do a translational coordinate transformation. And then on the other side, let's check the coordinate. So this sliding joint needs to connect it to your link number 3. So we need to make sure that your link number 3, the length direction of your link number 3 is actually a z-axis. So let's find your link number 3 coordinate, and you can see that the direction of the length or the sliding motion we want is not along z, it's actually along x. That's not good. So hence we have to do some rigid transform. So as I mentioned before, we can use rotation to change axis. You select align axis because we don't want x motion, we want z motion. So your x becomes z and z becomes x. And in such a way, we can connect your link number 3 and the prismatic joint. You can check it out. And you see that Simscape doesn't really like it. It says model not assembled. That's usually the case when your coordinate systems are not correctly aligned. So whenever you see an error message like that, what you need to do is you need to go to your Mechanics Explorer and find the tools, and in the end you can find a model report. And then here it's going to show you which joint that's giving you this error. So here you can see that the sliding motion is not correct, or the prismatic joint is wrong. So that's why we have to focus on the coordinate system of your sliding joint, and then we can see the base, something like this. Your follower is something like that. So okay, we find the problem. So in this case, you can see that the z coordinate, they are aligned, but then the xy coordinate, they're not, right? So that's why we need to do something in these location, or for either for the base, or we need to do something in here to change the follower. So here I'm going to show you how to change the coordinate here. So that means we have to change our base coordinate such that it aligns with your follower coordinate. So if you look at it here, compare these two coordinates. In order to move here to here, what we need to do is we actually need to rotate everything around z-axis clockwise by 90 degrees. Okay, so that's why we need a rigid transform. And then you get double click, go to rotation around standard axis. Everything is around z direction, z-axis, and it's clockwise. If you look down, so if you select z positive, that means you're actually looking down from the z positive direction, and then the rotation is clockwise 90 degrees. So that means it's minus 90. That's because clockwise always means negative, and you can click apply. And if you drag these and then click run again, you can see the error message is gone, and Simulink likes your setup. So in the next step, we need to assign the input to our blue link. So what you need to do is double click your O2, select actuation, the torque is automatically computed, and your motion is assigned by input. And we know that our motion is a constant speed, so the displacement is a ramp function with a slope of theta 2 dot. Click OK. Because your ramp is a Simulink function. In order to connect it to a Simscape, you need a converter. And then since you already have this converter, you need to assign a unit. By default is 1. You need to change it to radian. And then your input handling is filter input. You select second order filtering and click apply. And then up to this point, you can click run, and you can see that your crank slider inversion is actually in motion. So next, we want to know how much torque we need to apply to drive this mechanism. So because that's our input torque is generated around your joint O2, so that's why we need to find your O2, go to sensing, and then in the end, you can find actuator torque. Click apply. After doing that, there is a torque output. You connect it to the scope here, and then click run again. And then that's your torque output. You can see that there is a very high spike. There is a very high spike at the beginning, but that shouldn't be true. The reason why we got this high spike is because of these filtering. So in MATLAB, when we create a ramp function at time equal to 0, and these filtering would not work very well because there is a sharp turning point in your function, and then at that point, the function is not differentiable. So in order to smooth out these numerical error, so what we need to do is we need to change the filter derivatives to provided by inputs. So in this way, we're providing both second and first derivatives by inputs, and click apply. So after doing that, you can see there are 2 more input ports. The second one is a velocity, so it's a constant velocity, so we need a constant. And then the velocity is theta 2 dot. Click OK. And then the last one is acceleration. So acceleration is also a constant, and it's a constant of 0 because it's constant speed. There's no angular acceleration. So we connect everything in this way, and then we can click run. So then if you check your torque, you can see the spike is gone, but then you are getting a very coarse torque input. That's because your simulation resolution is not high enough. So you can go to the gears and then find the solver details, change the relative tolerance. You can change it to 1e minus 9. Then click apply, OK, and give it another shot. You can see that right now your torque is very smooth. That's what we want.